Okay. Yeah, hi everyone. I'm Zhijian Liu, and I will be TA for this course along with Eugene Lin. And today I will be giving you like a quick live Collab tutorial on how to train deep neural networks using PyTorch. And also how to like download the lab assignment as well as how to submit it after you finish it. So this is the Canvas page. Hopefully everyone has access to it. So if you have any issues with that, feel free to let us know so we can take a look together. So on the left-hand side, you can see there are a few tabs. So let's go to the assignment tab directly. So here you can see there are a few upcoming assignments, including some labs, paper reading presentations, and also the final projects. So this will be the central place for us to like access to these materials and also submit assignments. So let's go through the lab 0 together today. So this will not be graded. It's just for demo purpose. So we'll actually walk through it together. And after a lecture, if you're interested, you can also go through the whole process for it as a test. So for each of the lab, we will provide a Google Colab link here. So basically, this is where we are going to work on our homework assignment. So let's click this link here. All right, so inside the Google Colab, so basically you will see it's pretty similar to the Jupyter Notebook, if you're familiar with that. So your local computational resources to run these jobs. So after entering the Collab, the first thing I would recommend you to do is to like have a copy on your Google Drive just as a backup, and also double check here the runtime type to make sure that you're running everything on the GPU because we're going to train the models on the GPU. Okay, then let's get started. So in this tutorial, we're going to go through the training, some like basics of training deep neural networks using PyTorch. There are other deep learning packages as well online, for example, TensorFlow, JAX, MXNet. So hopefully these basic concepts can also transferable to other deep learning packages. But in our course, we'll be mainly using using PyTorch, like for the next few labs as well as for the final projects. So let's first go over the setup part. So we'll install a few packages that we'll be using in the tutorial. Because actually Collab has pre-installed a lot of packages, including the PyTorch. So here we only need to install the torch profile, which is a package to calculate the number of max for the model, which we'll be using in a few minutes. And we'll then import a few libraries, like some system libraries, like some PyTorch libraries, as well as like here we import the matplotlib, which is used for the visualization purpose. To ensure the reproducibility of the deep neural training, control the seed of the random generators. So it's important to make sure that you set the seed for all the packages that like introduce the randomness. So basically they're like system level random package, they're NumPy random package, and also the torch. So even if you set these seeds, the training behavior is still not guaranteed to be the same after multiple runs. This is because when you're training the models on the GPU, NVIDIA GPUs, you will be using the cuDNN for the training, and the cuDNN has some like stochastic behavior. So PyTorch provides some knobs to actually partially control that behavior. So I'm not going into too many details, but if you're interested, you can refer to the official like documentation to see more details. All right, so the first part of the deep neural network training flow is to define the data. So in this tutorial, we will be using the scikit-10 as our target data set. So this data set contains 10,000 images from 10 classes. So basically the goal for the deep neural network is to classify each image into like one of the 10 classes that the image belongs to. And for each image, the size is like 3 by 32 by 32. So 3 is the image channels, RG and B. So height and width. So let's quickly take a look at the implementation here. So before defining the data set, we need to actually first define the data transformations we're going to apply onto the onto the input images. So on the training side, we will apply a few data augmentations to like increase the diversity of the data during training. So we apply the random cropping augmentations. We also apply the random images left and right with 50% of probability. And also at the end, we also do the two tensor basically to transform the data from the image type to the tensor type that can be directly processed by the PyTorch model. So with that, then we can define the training and testing split of the Scify10 data set here. Basically, we construct the Scify10, sending the like some arguments like the root, basically where you're going to store the data set, the train, the transforms we just defined. And then we can visualize the data set a bit to see like what does the data look like. So actually I have pre-run one of the notebook before, so we can just directly take a look at the results here. So here are the results from the some sample data from this data set. You can see for each column, it corresponds to a different class. So it's actually much harder than we might thought because actually the image resolution is pretty low. So actually even for human, we cannot really like guarantee to get like 100% of accuracy. And also for some classes, they're a little bit ambiguous to each other, especially because the resolution is very low. For example, the automobile and the truck, and also the airplane and the birds. Like for example, for this particular example, it's not that easy to actually distinguish. So to train a neural network, we don't really want to like go over the data one by one, but we actually want to feed the data in batches. So in order to do that, PyTorch provide a data loader class we can use to wrap the data set, specifying the batch size we're going to use, whether we are performing the shuffling, and also the num workers we're going to use. So here we set the num workers to 0 because Collab does not have a very strong CPU. But if you're going to run the jobs on the lab servers, for example, right, you can increase this number to a larger number so that you can make use of the multi-processing to speed up the data loading process. With the data loader, let's take a look at the data type and shape from the training data loader. So you can see here, like for the input, the data type is like 32-bit floating point, and the shape is 512 by 3 by 32 by 32. So 512 is the batch size, 3 by 32 by 32 is the size of the input image. And here for the target, like the data type is the like a 64-bit integer tensor. So basically it's an integer from 0 to 9 indicating which class like that particular image belongs to. So that concludes the data part. For the model part, in this tutorial, we're going to use a variant of VGG11 as our model. So because like for the VGG11 model, Professor Han just described earlier in this lecture, is that data set. So the input resolution is much larger. So in order to make it fit for the smaller like image, for example, from the Scify dataset, we need to remove a few downsampling layers and also using a smaller classifier to like prevent overfitting. So for the model definition part, let's quickly take a look on how we can implement a model in PyTorch. So basically, we need to define a class. So here we define the VGG class, inherited from the PyTorch nn.module. And then at the very beginning, we define a constant architecture here. So basically, it's a list of layers in the backbone. So here you can see in the list, there are like numbers and also characters. So for the numbers, it's basically indicating a conv bn relu block, and the number indicating the output channel of the convolution layer. And for the character m, it's basically a max Boolean layer with a kernel size of 2. So with this defined, we can then like construct the layers one by one. So basically, we'll go over the list one by one, and if it's a number, then we just construct the conv bn relu layers one by one and add it back to the model. So for the convolution definition, you need to send in the input channels, the output channels, which is x here, and also 3, which is the kernel size we're going to use. as well as the padding size. We set the padding to 1 because we want to make sure that output size is the same as the input size after the convolution layer. And also the batch normalization layer and the ReLU layers, they're pretty much the same. Similarly, we can construct them. And for the max pooling layers, we send in the pooling size here, which is 2, and use that to construct that layer. All right, so with all the layers, then we can wrap it up with the n-n-dot sequential. So basically that tells the models to run these layers one by one. So the output from the previous layer will be the input to the next layer. And similarly, we can define the classifier, which is a single layer fully connected like layer, projecting the features from 512 dimension to 10 dimension, corresponding to the 10 classes of this like data set. So for each model on in a PyTorch, we need to also define the forward function. So basically that controls the like how we want to execute the computation of that model. So basically, given the input tensor X, we'll first send it into the backbone. So the input to the backbone will be n by 3 by 32 by 32. So n here is 512 in our case, but the model can actually adapt to different batch size. And for the output of the backbone, the size is n by 512 by 2 by 2. The reason here why it's 512 is you can see from the architecture list. So the final convolution layer has an output channel of 512. And here, the spatial resolution is 2 by 2. That is because you can see there are 4 ends in the architecture definition here. So that means for each max pooling layer, it will downsample the data by like 2 times. So in together, it will like downsample the data by 16 times. So 32 divided by 16 would be 2, so it's 2 by 2. And after that, we apply the average pooling onto the features from the backbone to squeeze the spatial dimension. And finally, we send the squeezed feature back to the into the classifier to get a final classification output. So the output will have the size of n by 10. So basically, it's a probability vector indicating the probability of like the instance being classified to each of the class. All right, so with the model definition, we can then instantiate the model and copy that to the CUDA so that we can train the model on the GPU. So let's quickly take a look at the model definition here. So there are a lot of layers. If you like carefully count the convolution layers, there are in total 8 convolution layers and 4 max pooling layers. And also we can do the same for the classifier as well. It's basically a single linear layer. So as this course focuses on efficiency, so we will also inspect the number of parameters and also the number of max for this model. So the model size can be estimated by the number of trainable parameters. So the implementation is actually pretty straightforward. We just go through the model parameters to check whether like each of the parameter is trainable, so whether it requires gradient. And then if it's trainable, then we just add the number of elements for that parameters into the counter. For this particular model, the model size is like 9.2, has 9.2 millions of like parameters. And for the computational cost, the max computation is much more complicated. So we will use an external package called PyTorch profile. So basically, you can just send in the model and also the input to that model into that function so that it will directly return the max. So you can see for this model, the total max is around 600 millions, which is actually pretty large. So in the next few labs, we will work together like using techniques including pruning, quantization, new architecture search to drastically improve its efficiency while keeping its high accuracy. And also there are a few details we need to define here for the optimization. We need to define the loss function because it's a classification problem. So the loss function we use is the cross-entropy loss. And also we need to define the optimizer. So we will be using the SGD with momentum as our optimizer. So the definition is pretty straightforward. We just define the SGD, sending the model parameters, sending these hyperparameters, the learning rate, the momentum, the weight decay. And then we also define the learning rate scheduler. The reason for defining that is that we don't want to use a fixed learning rate across the training. We want to adapt the learning rate across, like along the training process. So the learning rate scheduler we'll be using is something pretty much like this. So the reason of using that is that it's proven to be very effective for faster convergence on Scikit-10. Originally on Scikit-10, it requires like hundreds of epochs to converge. But with this particular like scheduler, we are able to train the model in only 20 epochs. All right, so with all these preparations, then we can start define some related stuff for training and evaluation, and then finally train the model. So for the training part, we need to define a training function that optimizes the model like for one epoch. So by one epoch, I mean it's basically a single pass over the entire training set. So here you can see the training function takes in, like, for example, the model, the data loader, loss function, and some other like optimization related objects. So the first step in the training function is to set the training mode, the model mode into the training mode. That is because some like layers in the neural networks have different behaviors during the training time and during the evaluation time. For example, for the batch normalization, during the training time, we will collect these running mean and standard deviations. But during the evaluation time, we will directly use these collected statistics from the training time to normalize the data. And also for the dropout layers, the behavior is also different. That's why we need to specify which mode we are going to, where the model is in for the upcoming operations. And then we go over the training data loader. And so for the training, for each training step, we move the data from CPU to GPU, reset the gradients, and run the forward inference, basically to run sending the inputs to a model to compute the loss function based on the outputs and targets, and then do the backward propagation. So that's actually being automatically handled by the PyTorch, so you don't need to calculate the gradient by yourself. And then finally, you need to update the optimizer and the learning rate schedule. And similarly, you can define the evaluate function. So I'm not going to like too much details here for the evaluation function. It's pretty much similar. So you just also go over the testing data set and also calculate the metrics. So with that, then we can start the training. So basically, we will train the model for 20 epochs. For each epoch, we are going to first run the training and then do the evaluation. So here you can see like the results after each epoch. You can see the accuracy improves from 22% of accuracy all the way up to around 93% of accuracy. The whole process will take around 10 minutes also on the Google Colab. And finally, we can visualize the model's prediction to see how the model truly performs. So you can see here, these are the 40 examples we pre-stored. For demo purpose, you can see for these 40 examples, only one of the examples are misclassified, which is this one. It's originally a bird, but being classified to a ship. All right, so that concludes. So that concludes the tutorial part, and I will quickly show how you're going to submit your homework. So basically, on the Google Colab, you need to make sure that all the outputs are in the Google Colab, and then you export the Google Colab to an IPY notebook. So basically, click download here and download the IPY notebook. And then let's go back to the Canvas page. For this lab assignment, you click the start assignment and submit the IPY notebook. So yeah, that's it.